Uh, Good morning, everyone. Happy to be here talking about how do you communicate machine learning models. Let me start with a small story on how I got started thinking about this problem. I've been doing machine learning for about 12 years now, but then the thought of visualization started, and I was trying to tell this story to my kid. If it had been today, it would have been revolving around Pokemon, but since this started a few months ago, this is about six blind men. Some of you might have known the story before, but they get to see an elephant, but they can't see, so they get to feel the elephant. So that when they feel, they touch, and that's how they collect data. This is a huge tusker, right? So there's a guy who's on the top, who's touching the body, who feels it's like a wall. So he screams, "Oh, I've seen a wall, I've seen a wall." The other guy looks at the huge legs, and touching it, he tells that, "Oh, this is very hard. It looks like a tree's bark. So this is a tree." And different guys tell different things. The guy at the back looked into the tail and told it's a rope. There's a guy in the trunk. He looks into it and he tells it's a snake. So there are different people telling different things for the same thing. That's how we have things, particularly in the industry where we build models. This is very commonly told to people who practice machine learning, that all models are wrong, but it's just some of them are useful. So it's about figuring out those some of them. How do we figure it out is what I'm going to give some intuition about in this talk. Having said this, I want to set a context that not all applications that require machine learning are big data, and almost not necessary that precision and your high accuracy is what drives the desire to do a machine learning model. A lot of applications where insights are more important, drivers are more important than accuracy. What do we have? We have data. Data is nothing but a clue to the truth that we want to find, that's being told by the data. This is what we're trying to do. We have data. We're trying to make sense of the world that we live in using a data lens, if you may say. Using that, we build a model, which is just an abstract representation at some level on what we think reality is and what machine learning tells us. What we need are a set of tools that helps us transition this implicit knowledge. So the moment we start talking about machine learning, we already have a sense that these are the things that might impact this business, these are the things that might impact someone's behavior. So there are a lot of things that's told by the data, but there's a lot more things that's sitting inside people's head, and you want to formalize that into an explicit model. So roughly speaking, like three major things. Actually fourth, I'll talk about the three major ones here. Want to talk about model complexity. So you want to know how increasing models complexity challenges the way you do machine learning. It could be simple things like, okay, what's the impact of regularization on my model? It could be complex things like, what if I use a deep learning model versus what if I use a simple decision tree model? You'd also want to understand, based on the different models that you fit, how accurate you get your models to be. And almost invariably, across domains, people want insights. So if you look into healthcare, people are more interested in, okay, what's the causal mechanism of the medicines the drugs being produced, things like that. Sometimes you also want to visualize it so that you can convince your boss. You would have spent months working on that. There are three major components that you do when you do machine learning model. You have data. You do a lot of data munging, data wrangling, to get from raw data to a representation of data that can be used for building the models. You would then explore the model using a lot of visualization techniques. Once you have that, you will end up building a machine learning model. The challenge is this, that when you do exploration or when you do a transformation, you always visualize, you see things and understand what's happening. But invariably, when you build a model, it never happens. It's generally summarized metrics that's being looked at. Okay, what's the cross-validation score? How did it perform on the test data set? What's the root mean square error? What's the precision? What's the recall? But there's been no emphasis on visualizing the output, the model itself. So I'll motivate an example of how we can go about visualizing the model output. Let's think about a simple case where, say, a pension fund wants to do a trading strategy. They hold a lot of stocks in a particular company, and they want to figure out if they have to buy, hold, or sell that particular stock. They have 1,000 stocks with them, and each stock is priced at $100. That's what they bought it at. Let's assume that there are like 500 minutes in a day for trading. So these are data. This is the data that we have. So this is the data that we're going to use to build a model. It tells the price variation in a particular day or 500 minutes. We run a machine learning model. We get a simple strategy that for every minute, if the price goes up by 5%, then sell one share. The price drops by 5%. Use something called a martingale strategy. We double down and we buy a share. If it's between that, you hold on to the stock. You don't act anything. Okay, now we have a model that's in place, and we have a data. Can we visualize the model in the data space? This is what happens. So this is how on the data that you have here, if you follow this strategy, you would end up with approximately 750 units at the end of the day. You would have sold about 250 units. How do we backtest the model? How do you do other stuff? First thing you would do is to vary model parameters. The parameter here was that 5%. If the price goes up by 5%, or if it goes down by 5%, you're going to buy or sell. We're going to go ahead and plot for all possible combinations, 1%, 2%, all the way to 10%. These are all possible combinations that can happen on your model parameter space. You could also change the models. Instead of selling something for every minute, you can go and sell every 2 minutes. So you can look for a 2-minute period and then sell if it goes up by 5% or 10%. It's the same set of plots for 2 model strategies with 1% to 10%, so you have 20 plots. But then you want to also check on unseen data, data that you don't have. When you don't have, what do you do? In something like this, we'll talk about strategies and what to do, but let's assume that we have simulated 5 data sets. You run the model and check what your model's visualization is across the various dimensions that we just talked about. And we use this to infer insights into the robustness of the model, what kind of things can we expect. Summarizing, these are the 5 major things that you would look into when you visualize a model. You want to visualize model in your data space. You want to change your model parameters. And when you fit your model, you want to fit across different models. So you could try linear regression, logistic regression, random forest, neural networks, and you would also do it across different data sets. Visualization is an art, it's not really a science. So there's a lot of techniques, so you have to figure out how you can use visualization techniques to represent this. Some things are easier, but as you grow across multiple dimensions, it's going to get extremely hard. When you do feature selection, dimensionality reduction, these are techniques that can be used for visualizing your model on your data space. If you want to change model parameters, the thing that you would do is hyperparameter optimization. You would visualize cross-validation, your metrics, precision, recall, whatever metrics that you're going to be concerned about in your model fitting space. You would do an ensemble of models to figure out what you want to select. And the technique to select different input data sets is to bootstrap. Now let's look into how we can do across multiple dimensions. In 2D space, it's really easy. So let's take an example, the same example. We continue that instead of price, we also take volume into account and we build a model. And here it tells strategy, so it's easy to visualize in a 2D with 2D space to whether to buy, hold, or sell. But the moment you get into 3D, it gets slightly harder. You need to do a 3D plot. But if you want to do for n-dimensional space, 2, 3 are things that we can comprehend. There are broadly 2 major techniques to visualize at n dimension. One is projections, simple projecting it to a 2-dimensional or 3-dimensional space. The other thing is something called tours, where you collectively change your features and visualize them. A simple example is this, where you rotate your entire model. This is still 3-dimensional, but this is just one plot. But as you keep rotating this, you also will have other features that you would rotate, and you would get to see which particular location, or which particular feature space your model works fine, and where it breaks down. It gives you insights into your model building process itself. The cool thing is, this was done in Matplotlib. I'll show the code in a little while. For the other thing is, you can reduce your data using principal component and then plot the principal components and show the model like this. Not necessarily you learn any insight from this. So it's not that all visualizations will lead to some insight. You can also have something like this where some of the previous plots had better insights than this. So the goal is do something similar for all the 5 things that talked about. Next is model parameters, or for various hyperparameters, again do 2-dimensional, 3-dimensional, change the parameters. It's easy to do for small to medium-sized data. For big data, you might probably want to sample to get a sense of how this happens. This is an example where we had the same model, had threshold on what the corresponding competitor's price was between 112 and 114. It completely changed between these 2 numbers. So you get a sense of where the model's transitioning from one state to the another. Same thing, so it's easy to do for 1-dimensional, 2-dimensional, but extend it for n-dimensional. Same thing for evaluation metrics. So you can do cross-validation, precision, recall, same sort of stuff. This is a very, very important thing when you build classification models. You want to know your decision boundaries, boundaries where your models break. There are two approaches. One is boundary line, the other is regions. This is the region approach where you simulate data. You don't take, so your features have a range as input space, maybe entire real line or a range where it can take data from. And you sample data from each of your features and you use your model. And these are the outputs that you see in your model. And you see 3 different colors which tells for the 3 classes. And you know that these are the places where it's strongly one class, strongly other class, and just like some overlap between the classes. The other option is to do just boundary lines. That's relatively hard because you need to find, this is called mesh grid. So you create a mesh grid and you sample your entire spectrum of data and do it. When you do for boundary lines, you need to find places where the probability between the classes are nearly 50%. That's where the model is having trouble demarcating the regions. That's relatively harder to do. Talked about bootstrapping to get different data sets and then run it on the same model to see how your model performs. Just summarizing, these are the things that you would do to visualize on data space, model parameters, model fitting, different models, and different input data sets. The entire code that was all done just through matplotlib. The entire code is right here on how the price data is obtained and what are the other features that you have. What's the model that was done, and interestingly, we can even do 3-dimensional plots over here. It's here. And then there's support in plot 3D for doing rotation of the entire model space. We are working on an equivalent tour implementation. That's at least a few months away. This is like some code to get started on how to do the stuff that it gives a GIF which can be embedded in the presentation. It's all just matplotlib to get the visualization, to get stuff. Yep. Yeah, the entire code is there on the GitHub repository. You can look into it, see various strategies on how to visualize once you build a model, to get feedback on what works, what doesn't work, and where to improve. Yeah. Thanks. Yeah. Questions?
How have you found working with 3D in Matplotlib? Have you found any other tools for doing good quality 3D visualization?
The question is, any other tools that we found that's good apart from Matplotlib? So in general, for model visualization, R has a lot more capabilities. We're trying to port some of those things into Python. Sometimes just use SciPy to visualize it in R itself. But that's particularly in, so there are a couple of packages in R which are really good. One is Tour, the other is a recent package called Broom, which summarizes the model summaries very well. And you can use that to, it's called tidy data. It comes in tidy data format, which can be used for visualization better. Those are things that I think can really help understanding models better in places where it breaks rather than just going with a cross-validation score, things like that. I haven't yet explored HoloViews and Bouquet, so maybe they might probably be better doing this, probably spend some time doing this and figure out if that works.
Let's have a seat one more time.
Okay.